All right, hey, welcome here. We're at day 3 here for summer school, and oh, hey, Ron, we should do a mic check. I don't think we did before we started the camera. Let's just double check that before we roll too far. All right, looking good. All right, so we have been working, as you know, into chapter 3. This is day 3, and so let's finish up chapter 3 here. In fact, why don't I take a moment to just point out, if you haven't been looking too closely at the syllabus, that we are right here on Wednesday, and it says we're going to complete chapter 3 and get started in chapter 4. And keep in mind, Monday is a holiday, and so over these next couple of days, I'll probably shoot you out a couple of emails, and I want to get that Canvas page a little more organized, and I want to post some solutions for you so you can check your homework. And in fact, I've got a bunch of great questions by email, and so keep them coming. But one of you said, you know, how can I check my homework? And you know, in preparation to make sure you're doing things right to get ready for the exam. And that's what I wanted to point out here, is that's what we're working for. These first 2 weeks, we will have an exam on June 1, and that's when all your labs and your homework will be due. But that email was great because it made me realize, wait a minute, yeah, you need a way to kind of check these to make sure you're doing things right. I know there are solutions to the odd ones in the back of the book, but I think I can get access to a solution manual and share that with you. And so that's my answer. And so after we do our lecturing today and the lab today, I'm going to look into that. So be on the lookout for an email from me because I want to get the solutions to you. And I want to set up a few other things and give you more information about how to get a hold of the tutor. Remember, the tutor is available, our local one, and I wanted to double check that. I'm pretty sure it was 11 to 1 every day. And things are now getting up to speed, and so now that we're getting into more significant homework problems, I would suspect that you are going to have some questions for the tutor. And of course, there's also the net tutor on the Canvas, which is the nationwide one. But our local one, even though it's only a 2-hour window every day, it is at least every day, and it is a good student who went through our program and went through this class, and you know, so knows exactly what's going on with this class. All right, well, with all that in mind, let's jump back over here to what we put on the board yesterday, and I just kind of left it here. I erased the rest of it, but chapter 3 was called Explaining Motion, and it is about Newton's 3 laws of motion. And so if I grab my notes here, you might recall we started by saying, okay, what is Newton's first law of motion? And the first law of motion we called the law of inertia, and that was the one that we basically said it tells us whether something is or is not accelerating. That is, an object at rest wants to remain at rest, and an object in motion wants to continue in motion unless acted upon by this net force. So we spent a lot of time there. We were working on in the second law, and the second law is more of a mathematical question. It says, or I should say, it picks up where the first one left off, because remember, the first law is basically telling us whether there is or is not an acceleration, and so we can look at something and we see if it goes faster or slower or turns. And maybe that's worth beginning to point out now, because we're starting to get to more advanced things, and you're going to see that in the second lecture of today. We're going to get into motion of two-dimensional space. And so remember, back in chapter 2, we defined acceleration as the change in velocity. And if you also remember in chapter 2, we said that there's a slight subtlety between velocity and acceleration. And I'm pointing that out, I mean, between speed and velocity. And I wanted to point that out now because acceleration is the change in velocity, not speed. Speed just goes bigger or smaller. But velocity also has direction. And so if you define acceleration as the change in velocity, then an acceleration could be something going faster or something going slower or something changing directions. And that's maybe a little premature, but is going to be emphasized as we leave this chapter and get into the next chapter. All right. So coming back to here, this first and the second law really tie together because, like I said, if we're doing this first law, if we see something go faster, or if we see something go slower, or if we see it change directions, right? That's why I mentioned that one. We know then there is an acceleration. Or to do any of those things, that is, to go faster, or to go slower, or to change directions, to do any of those would require then a force. And so that's what that first law was saying. And so that's what we talked about last time. And then we saw, and we're going to continue on here today, that we can then calculate that acceleration. And so if we know something is going to have an acceleration, or if we know it does have an acceleration, we could either calculate its acceleration, or if we know its acceleration, calculate its net force. And this is the mathematical equation. And so the second law, like I keep saying, picks up where the first one left off. The first one tells us, is there or is there not an acceleration? And then the second one tells us how we could calculate the value of that acceleration. And as we'll see, also the direction. And so we'll start doing this. We'll start putting an arrowhead over these guys. And we'll start saying, hey, these have a direction to them. What direction is real important. And that's where I want to pick up here today. If you remember yesterday, I did some problems like this. I was setting up the cart, and I was putting in the plunger. Maybe I'll just put it on its, well, I'll go to the full setting, why not? Put it at its full setting. And we gave it a little push like this. And the thing rocketed on out. And what was happening is it was getting a force towards, my right, your left, but my right here, and it accelerated in that direction. And the reason that is important is because to talk about net force, I'll just say the net force is really the result, if you will, of all the forces. We like to say it's what you get when you combine all the forces together. And I'm deliberately staying away from the word adding them together. Because yesterday, I'll say it again, all I had was one force. And I said, when we push this plunger all the way in, I said, okay, this will give me a force of 3 newtons. And just to recap, what I did is I did something like this. And if you'll let me do a little drawing, here's the cart. And I said, okay, now there's a push. And so if I label this push as 3 newtons, and I remind you that the cart has a mass of 1/2 kilogram, I did something like this. I said, okay, well, the net force is 3. And let me pause right there, because that's where I want to extend on from yesterday, is that this net force is the combination of all the forces on this object. But yesterday we did the easy case. Yesterday we did the case where there was only one force. And so it's kind of like probably how you make money and stay alive in this world and pay your rent and buy your food. You probably have more than one job, and you do a little here and a little here and a little here. And so your total income for that month is the combination of all of those. And your net income then is the combination of all those jobs then minus all of your bills. And so you probably have 2 or 3 little jobs, and you combine those together. Then you pay out your rent and your food and your school tuition bills, maybe a cable bill, maybe a cell phone bill, maybe an insurance bill. You get my point here, that we got to combine all of them together to see what is the whole net effect at the end of the month. And that's what I'm saying about motion here. Motion, we have to put all the forces together. And so when we had something as simple as this yesterday and we just release it, we just go, oh yeah, well, whoops, I keep forgetting it's not a bumper. All right. But when we put all those together, and in this case there's only one, we get this 3 newtons, and so we did something like this, and we came up with this answer. We said the acceleration is 6 meters per second each second. And so that's still true, but here's where I want to change. Here's where I want to go one more advanced step that is really Newton's second law, and it's the reason we like to put a little arrowhead over here, because we like to say the direction matters. Now, we touched on this in chapter 2, right? What was the difference between speed and velocity? And you might remember that silly story I said about the international traveler who comes here to Santa Barbara, and you tell them to get in the car, get on the freeway, travel for 2 hours, and they'll be in Los Angeles. But what you don't mention is to go southbound, and the travelers go northbound. And I was asking, does direction matter? And hopefully the answer was, yeah, definitely matters. And I want to emphasize, yes, it does. But I would say there's a lot of quantities in physics where the direction does matter. And a force, a push or a pull, does matter. I mean, if I walk over here to this door, and I get to this door, does it matter if I push or pull on the door? Because if I pull on the door, something different happens than when I push on the door, right? The direction of the push does matter. If I were to come over to here, and to get further to my point here, let's say there was 2 of us up here, me and a friend. And if I push this way, which in our setting that's west, so if I push west and my friend pushes west, that is one result. And a different result would be, what if I still continued to push west, but my friend gets over here and pushes east? Or for that matter, they could even still stand next to me and they could be pulling towards the east. Do I get a different result here, a different outcome? Yes, and in that case, my friend is opposing the direction I'm trying to push. Or you might say, we're not working together as a team. And so I'm trying to say that the direction of the force really matters. And so if I can use some fancy words here, let me use the word vector versus scalar. See, a vector is a physical quantity that has both a number and a direction. And since you started school way back in kindergarten, you've been learning about just numbers. You probably never used the word scalar, but that's what we mean by the numbers. Just a scalar. A scalar is just a number. And there are some quantities in the physical world that the direction doesn't make any sense. For example, time. We've already been talking about time is a scalar. You know, you don't ever say, hey, we've got 10 minutes before our break, but it's 10 minutes to the east, as opposed to 10 minutes to the west. It doesn't make any sense. It doesn't have a direction. It's just a number. It's 10 minutes until we break. Not 10 minutes to the east, not 10 minutes to the west. It makes no sense. Another one that you're probably familiar with is mass. We've mentioned it a little bit. We talked about it already. We did these calculations. It's just, again, a number. This right here is even labeled. It has a mass of 1,000 grams. As I said, this is a half a kilogram or 500 grams. These two are 500 grams or a half a kilogram here. But they're just a number. Oh, we don't say this has a mass of 500 grams to the north or to the left. It makes no sense. Okay? And so some things in the physical world are really just about numbers. I'll give you a third one and I'll stop because I think you're getting my point. But temperature would be another good example. You know, we can look outside here and say, you know, the temperature is 75 degrees Fahrenheit. So we do have units. I should emphasize that. And these numbers are the stuff that you've been doing since, you know, elementary school. Just a number. Units go with those numbers, so don't get me wrong there. But they don't need a direction. But there are some other things in the physical world where you can't give a complete description if it is just a number. It has a number and a direction. It does matter. And so, like I said way back in chapter 2, velocity is a really good example. Because if you get in that car and go 60 miles an hour northbound, you will get a different result than if you get in that car and go 60 miles per hour southbound. If you go southbound, you get to LA. If you go northbound, you get to San Luis Obispo. And that was the silliness of my story. But it does matter. And the second one I'm trying to show you here is force. Forces have direction. They fit under this category of what we call vectors. It does matter which way you push on something. And that was my silly thing about pushing on the door, or my example of me and my friend here. If my friend and I push in the same direction, we get one result. If my friend and I push in different directions, well, we get a different result. And so very much, just as important as the amount my friend is pushing, the direction my friend is pushing really matters. You know, in fact, if I'm trying to move this whole table and my friend is pulling in the opposite direction of me, I would be better off not even having the help from my friend. My friend's not helping me, my friend is hurting me. And so their direction is just as important as their number. They might as well have no number. They might as well just sit down and rest while I do all the work. And so again, maybe I'm spending too much time here, but I just wanted to emphasize the direction that does matter. I didn't really focus too much explicitly on it yesterday, but I did have a little conversation, and I hope you caught it, that the direction of the acceleration was important. Remember we said if something is speeding up or slowing down? Maybe I would do something like this. Maybe if I put an object up here, and I'll just put a little baseball, because it's supposed to be baseball season. And if the object was moving this way, and so we say I'll put a little v here for its velocity, and if the acceleration, and so I'll put a little a, is in that same direction, we said this would make it go faster. But if you also remember, and this was right at the end of chapter 2, right, where I said, okay, we start with the ball and we throw it up. And I said, I throw it up really fast. I threw that, I think I had a golf ball in my hand, and I'm going to throw it up with all your might, and it goes upward at a speed of 30 meters per second. Well, 1 second later, it will change by 10, but it'll slow down by 10. And so the acceleration is down, but the object is going up. And so when we have an acceleration that is the opposite of the direction of moving, we get a result that makes the object go slower. And so this is my way of saying, we did mention this. We did say that acceleration is a vector. Now, I didn't use the fancy word vector till today, but the direction of the acceleration is an important part. And, of course, one that maybe goes without saying, but I'll put it anyways, is the position of something. And I think in yesterday's lecture I said the same thing that I usually say to a face-to-face class. I said, okay, when class is done, does it matter if you move to the west to go to your car versus going to the east to get your car? You don't want to just say, well, my car is a half a mile away, so after class I have to go walk a half a mile. It matters whether you walk a half a mile north or a half a mile south or a half a mile east or a half a mile west. The direction does matter. And so position is also a vector. And so you're getting my point, and you'll see as we go along that when we get to new quantities, and so this chapter, the new quantity is right here, and I'm trying to point out that force is one of these categories called a vector. Its direction does matter. And I bring it up now because I'm trying to go a little bit deeper into Newton's second law, because what we need to do is figure out the net force. And as I was saying, the net force is the result of all the other forces. And here's something that we have to keep in mind. It's not just the magnitude of the force, but it's also what direction is that force. And that's where then it becomes a little more complicated. And because of that, I think it helps to do drawings. And so I'm going to encourage you to do drawings. In fact, I'm going to demonstrate them now. Most of them, my ability to think and my ability to get you to do some of these calculations will involve a drawing. Because a drawing is a really good way to have the number, but also keep in mind the direction. It's why the lab we're going to do today. And when I film that lab, one of the things I'll say at the very beginning is watch this lecture first before you go do that lab. Because today's lab is going to be an exercise in these drawings. And it will give you an opportunity. If I remember right, there's 5 problems in the lab today that says, hey, do these drawings. And then show that these drawings match the real world. And so we will actually set up forces and see that they match. So more on that when we get to the lab here. But for right now then, let me do something like this. Let me come over here and say, all right, what if I had a cart and both me and my friend are pushing on this cart? And so I'll just use this cart in the front of this room. It's actually a pretty heavy cart. It's something like 30 kilograms here, okay? And so let me just come over here and say, okay, I'm going to push this cart with a force of, I'll just say 40 newtons, okay? So in my diagram, I'm going to put an arrow here. And the arrow then is going to indicate the way I'm pushing it. And so geographically that would be west, but in this picture I'll just call it, that's the positive direction. All right, so this is 40 newtons. So I'm pushing with 40 newtons. But what would happen, and I'll start with the easy one here, if my friend, either next to me or on the other side, was pushing this way, to the east, which in my drawing I'll call that the negative direction. So my friend is pushing 40 that way. And this is where Newton's law, second law, becomes a little more I'll say useful, but I'll also say mathematically challenging, because you got to figure out then, okay, what is the net force? And again, I'll say the net force is the result of all the other forces that are going on. So you can't tell me the motion or the acceleration of this cart until you include both forces. And I think that makes sense. But also, you can't include the resulting net force until you also realize what direction they are. And I like to do this one first because I'm hoping this is pretty obvious. Well, here's what I would do. I'd say, okay, what is the net force? Well, I guess I have a positive and a negative force. I have a positive 40 and I have a negative 40. I have a 40 to the right and a 40 to the left, and that net force is 0. And so the acceleration would be, and so let me emphasize, what goes in the numerator is net force. It's not my force. It's not my friend's force. It's not the magnitude of them added together even. It's not 80. It's a combination of both of the forces, including the direction, as well as the number. And so what I would get here is 0. And then the cart would be 30 kilograms. But either way, I get 0. And so I would say the net force is 0. Well, that really is no different than what we did for the first law, right? The first law, this kind of looks like the first law. Because the first law, we said that to get an acceleration, you have to have an unbalanced force. And we really talked a little bit about this. We said this is a balanced force. Now, we didn't use the fancy word net force, and we didn't use the fancy word vector. But I think physics is best taught if you understand the concept. The big words are important to your education, but they're not really the knowledge. The knowledge is the ideas behind them. And so earlier on, we didn't call it vector, we didn't call it net force, but we did try to portray that this is a balanced force. And a balanced force would give you a constant velocity according to the first law. Constant velocity means 0 acceleration. So sure enough, this is really just I'll call a long way of saying Newton's first law. I've got a balanced force and I get no acceleration. That is, I get a constant velocity. So this is kind of the first step of getting you to hopefully see that the net force combines all the forces together and includes their direction. Because let me try a little different here. And I'll do it first with a diagram. So here's this cart again. And let's just say that I'm still pushing with a force of 40 newtons. Okay. And this time, my friend, is actually what I'd call is being helpful. My friend's actually pushing in the same direction. So I'll put an arrowhead in the positive direction. But they are pushing a little bit less than me. And so I'll just say 30 newtons. And so if I asked this question, what is the acceleration of this cart? And so let me come back here to what I'm trying to emphasize here, this calculation, right? Newton's second law. How do I calculate this acceleration? I need the net force. How do I get the net force? The net force is the result of all the forces. But remember, force has number and direction. So when I take into account all the forces, and in this case there's only 2 of them, but I think it illustrates it. We could have 3 or 4 forces, but if I have 2 of them, I would say, okay, my first force is 40 newtons. That's the force for me, so it's a positive 40 newtons, it's to the right. And the other force is also a positive 30. And so I would have a net force of 70 newtons. This is just another way of saying that the two of these forces is the equivalent of one force of 70. Exactly. And so the motion of this cart is determined not by one force individually, but all the forces are on it. So that's why we call it the net force. And again, also what direction they are. So these two, me and my friend, are the equivalent of 70. Now, of course, let me also divide that by the 30 kilograms. Let's see, 3 goes into 7 2 times and then a third. So this would be 2.33 repeating forever. And remember from yesterday, a newton is a kilogram meter per second squared. So the kilogram would cancel off, and I would get meters per second each second. So I would get an acceleration, me and my friend pushing on this, of 2.33. Now, let's try a little harder one, and maybe I'll leave this right here because I think that's worth keeping up, because that's what I'm trying to show you here is that the harder parts of Newton's second law is to realize that you need to get the net force. It's not just one force or the other, or the third if there's a third or a fourth, but it's the combination of all of them. And I keep saying combination, not necessarily add them, because watch this problem. What if I had a slightly different scenario? What if I had me, again pushing to the right with 40, and my friend pulling, and so the force is in the negative direction with the 30. So a little different than this one over here. But I want to emphasize, notice the numbers are the same, but the result is not, because again, force is a vector. And so it's real important that I get across to you that as we try to understand physics and we try to understand the physical world, it's not just the number, it's also what direction it's going. And that's that fancy word vector that has been introduced here today. All right, so if I go to calculate the acceleration of something like this, I would say, okay, I have a 40 newtons in the positive direction, and I would combine that with a 30 newtons, but the 30 newtons is in the other direction. You might say it's taken away from my 40. It's a negative number. And so that's how I would treat it mathematically. And that's again why I want to say it's the result of these forces. I didn't want to say you add the forces, because here I didn't add them, I subtracted them. In fact, what I want to emphasize is, how do I know if I'm supposed to add the forces, or in this case, subtract the forces? And that has to do with the direction. And that's why the picture is so important. So you'll see, I'll be teaching, and you'll read it in your book, and that's why we do the lab today, that drawing the pictures, drawing the arrowheads is a very, very useful tool. And we're going to do that over and over again. A lot of drawing of the arrowheads. Now, you may argue that the arrowhead, well, that's just a length. That's not a force. Okay. But if you remember over here on the board, one of the vectors was position. And so I would say that these arrowheads I'm drawing have to do with distance, have to do with positions. They are a vector. And if force is a vector, then the drawings of position will help me understand what the force result will be, even if I'm not really drawing forces. And so that's why, as you'll see in the lab today, you're going to be asked to do a lot of drawings. And you'll actually be drawing distances, but interpreting that as forces. And that's what I'm doing now. All right, so I've drawn arrowheads, which, like I said, are really arrowheads of distance, but they can be interpreted as forces. And so here I have a positive force and a negative force. And so if I put that together, I get 10 newtons. And of course, remember the cart is 30 kilograms. And so here I have 10 divided by 30, which is 1/3, so that'd be 0.33, repeating forever. And then the same idea, Newton over a kilogram is meter per second squared. And so this is the result I get. And notice, of course, it is a very different result than when they were in the same direction, indicating again, the direction is just as important as the number. You can imagine if my friend pushed more or less, this would change, and nobody's surprised that the acceleration then depends upon the number, and that is the magnitude of the force. But I'm trying to emphasize what is also just as crucial is the direction. And then you've got to draw these little pictures in order to figure out, okay, am I going to add them or am I going to subtract them? Now watch, let me try a third scenario here. All right, so here's this cart. And this time, let's say I'm only going to push with 30. So I'll reduce mine down a little bit. So I'm a 30. And my friend, if I can draw it on here, is going to keep pulling opposite of me, but I'm going to up my friend to 40, so we'll switch our numbers. What do I get? Well, acceleration equals, and then let me emphasize, what goes in the numerator right here is the net force. What's the net force? The net force is the results of all these forces. And as I've said many times, and I'm going to keep saying it here for another 10 minutes or so, just as important as the number is also the direction. Okay? So in this case, I would have a plus 30. So I've got 30 to the right, and I've got a minus 40, because I've got 40 to the left.